Hi there, my name is Zhou, and I'll be presenting our work on effectively localizing active objects in egocentric videos using symbolic world knowledge. This is a joint work with Ling and our advisor Violet at the UCLA+ lab. First, what exactly are active objects and why do we care about grounding them? Imagine you're wearing the next generation AI-powered smart glasses that can converse with you. The AI agent is trying to teach you how to cook a dish by instructing you with certain actions to take. In order to determine if the actions have been successfully executed, the AI will need to track and examine the pre- and post-condition states of key objects involved in the action. This includes the object undergoing state change due to the user action, and also the tool facilitating such state change. Let's take a look at another example. The action cut the pawpaw into half with a knife, where the object undergoing state change is the pawpaw, and the tool facilitating this state change is the knife. To localize and track these objects, the model must first correctly extract such entities. Then it should be able to ground them within the user's egocentric view. Here, the three images represent the user's viewpoints throughout the action process. In this work, we propose to leverage action condition symbolic knowledge of the active objects, thus providing existing phrase grounding models with continuous localization guidance. Furthermore, we utilize general object-level descriptions, regardless of the actions being performed, to enrich our symbolic knowledge. Next, I will introduce our tasks and datasets. We use two popular egocentric video datasets as test beds for our method. Ego4D is a comprehensive video dataset covering a wide range of everyday tasks. Epic-Kitchens is a similar dataset focusing on daily kitchen activities from the first-person view. For Ego4D, we specifically focus on its state change object detection subtask. The task defines three types of frames from a video concerning a particular human action. The PNR, or point of no return frame, is defined as the point where the action is just about to take place. Centering around this, the pre- and post-condition frames define the frames where pre- and post-conditions have been satisfied. In addition to state change object detection, our framework is also naturally suitable for long-horizon object tracking during an action. Here we leverage the Epic-Kitchens Track 150 subtask, where each clip focuses on a particular action performed by the human actor, resulting in a target object to undergo state changes. Notice that the object being tracked will sometimes encounter heavy occlusions and move in and out of the user's point of view. We later demonstrate that our framework is effective towards resolving this issue. Next, I will introduce our model structure. Our model is derived from the GLIP Open Vocabulary Object Detection Architecture. We enhance the GLIP model with LLM extracted symbolic knowledge, and further supervise its joint inference with a frame type predictor. Given a textual instruction as input, we first extract the key object that undergoes state change and the potential tool to be used. Then, we leverage LLM's common sense knowledge to generate visually recognizable pre- and post conditions along with object descriptions. Please refer to our paper for more details on this part. Next, we give a detailed view of our model architecture, starting from a GLIP model, which is pre-trained on word and image region alignment pairs to perform generic phrase grounding. We significantly enhance GLIP's abilities by providing it with detailed pre-post object state conditions and object descriptions extracted in our previous step. Unlike normal phrase grounding, which only focuses on the named object, here the object phrase and accompanying symbolic knowledge as a whole would be taken into consideration. On top of this, we learn a probabilistic frame type predictor to aggregate and then automatically associate symbolic knowledge with corresponding frames, enabling joint inference. Finally, let's take a look at our experiment results. For the Ego4D SCOD task, we compare our model against the best performing existing models on official metrics. Results demonstrate our model significantly outperforming both the state-of-the-art video intern model and the vanilla GLIP model across all dimensions. Ablations also showcase the benefits of including object descriptions and state conditions in the joint inference pipeline. For active object tracking with the Epic-Kitchens dataset, We test the capabilities of our model by replacing the detection verification module of existing trackers with our knowledge-enhanced detection pipeline. This results in drastic improvements in object tracking ability, as measured by standard metrics including success score and average precision. Our model is able to save the tracker in cases of object occlusion and distraction. We further provide detailed qualitative analysis on both success and failure cases of our model. For more details, please refer to our paper. In conclusion, we provide a novel LLM-enhanced approach for active object grounding in egocentric videos. We demonstrate the usefulness of our symbolic knowledge extraction and joint inference pipeline, state change object detection, and object tracking tasks. Thank you for listening.